All right, welcome to the Explainer. Today we're going to tackle a huge topic, the force that literally holds everything together. I'm talking about that invisible pull that keeps our feet planted on the ground and sends entire galaxies swirling in a cosmic dance. Yep, we're talking about gravitation.
So, here's the plan. We're going to start with a super simple question, then see how it leads to a law for the whole universe. Then we'll tackle the whole mass versus weight thing, and finish up by seeing how it all plays out across the solar system. Let's get into it.
All right, so our journey here, it doesn't start in some high-tech lab. Nope, it all kicks off with a really simple observation, a question that humans have probably been asking since, well, forever. I mean, just think about it for a second. You drop your pen, an apple falls from a tree, you let go of pretty much anything, and it goes one way, down. Always down. So what's going on here? What's actually causing that? Well, the answer, of course, is gravitation. It's this fundamental, totally natural phenomenon, this invisible pull that exists between any two things that have mass. And when I say any two things, I mean it. We're talking everything from the tiniest particles all the way up to giant planets and stars. And this isn't just about stuff falling on Earth. Oh no. This force is a long-distance player. Think about this. The moon is way out there, right? But its gravitational pull is so strong it reaches all the way here and literally tugs on our planet's oceans, creating the tides. That's pretty amazing. So how did we go from just watching things fall to actually understanding the rules of the game? Well, for that, we have to thank Sir Isaac Newton. He's the one who basically wrote the universal rulebook for gravity. So, Newton broke it down into two simple, really logical ideas. First, mass. The more stuff an object is made of, the more massive it is, the stronger its gravitational pull. Makes sense, right? And second, distance. The further away you get from something, the weaker its pull gets. And it doesn't just get a little weaker, it drops off really, really fast. And when you put those two ideas together, boom, you get this incredibly powerful formula. This was a total game changer, you guys. For the first time in history, a single equation could explain why an apple falls to the ground and why the moon stays in orbit around the Earth. It was like he found the one rule that governed both heaven and Earth. Just incredible.
Okay, but look at that formula. There's one really important piece in there, that big G. Now, this isn't just some random variable. It's a very specific, unchanging number called the universal gravitational constant. You can think of it like the master volume knob for gravity in the entire universe. It sets the strength of that force everywhere.
And just look at how small that number is. It's minuscule. That's a decimal point, followed by 10 zeros before you even get to the 6. That's why you don't feel a gravitational pull between you and, say, your remote control. The force is technically there, but because G is so tiny, you need a massive object, like planet-sized massive, for the force to become noticeable.
And here's the really mind-blowing part. They call it the universal constant for a reason. Its value is the same everywhere. It doesn't matter if you're on Earth, on the moon, or in some galaxy on the other side of the universe. It is a true, fundamental constant of our cosmos. It just doesn't change.
All right, so now that we have this amazing law, we can use it to clear something up, a thing that trips a lot of people up, and that is the difference between your mass and your weight. Because, spoiler alert, they are not the same thing. Okay, this is super important. Your mass, that's the amount of matter, the stuff that makes you up, and that number, it never changes no matter where you go in the universe. Your weight, though, that's something completely different. It's not about you. It's about the force of gravity acting on you in a particular place.
See, that gravitational pull causes any object to accelerate, to speed up as it falls. And we have a special name for that acceleration. We just call it little g. Right here on the surface of the Earth, g has a value of about 9.8 meters per second squared. You've probably seen that number before.
And that leads us to a super simple formula for weight. All you do is take your mass, which is always the same, remember, and multiply it by whatever the local g is. That's it! So when you step on a scale, it's not actually measuring your mass. It's measuring the force of gravity pulling you down.
So if G can change depending on where you are, what does that do to your weight? Well, let's find out. We're going to take a quick trip to the moon.
Okay, so here we are on the moon. It's way smaller and a lot less massive than Earth, so it makes sense that its gravitational pull is a lot weaker, right? And that means its G value is way lower. Look at that difference, just 1.63 compared to the 9.8 we're used to. Actually, there's a really easy way to remember this.
The gravity on the moon is almost exactly 1/6 the gravity on Earth, so you'd feel incredibly light, which is why astronauts can do those amazing bouncy leaps.
So let's really put some numbers on this to see what's happening. Imagine someone has a mass of 60 kilograms. On Earth, their mass is 60 kilograms. On the moon, guess what? Their mass is still 60 kilograms. That doesn't change. But their weight? Whoa. It drops from 588 newtons here on Earth all the way down to just 98 on the moon. Same amount of stuff, just a completely different force pulling on it.
And here's a cool little detail. G isn't even perfectly the same everywhere on Earth. See, our planet isn't a perfect sphere. It kind of bulges out at the equator. This means if you're standing at the equator, you're slightly farther from the center of the Earth than if you're at one of the poles. The result? Gravity is a little bit stronger at the poles, and you would actually weigh just a tiny bit more there. How about that?
So let's just nail this down one last time because it's the big takeaway. Your mass is you. It's the amount of you there is, and it's constant. Your weight, that's just the force you feel, depending on where you are. It's the relationship between you and the planet beneath your feet. And all of this leaves us with a pretty cool question to think about. If your weight is just a force that depends on where you are, could you ever really be weightless? What would it take to completely escape that pole and just float? Something to chew on. Thanks for joining me on this explainer.